Hey everyone, welcome back to Real Analysis 1. This will be lecture 9 of the course. And in this section, we're going to kind of finish up our large section on sequences with just an introduction to series of real numbers, which kind of is a natural follow-on and an enhancement elaboration of the idea of a sequence. So let's take a look at this. And again, this will be just an introduction to series. It could come up later in the course for sure, but we'll be shifting gears after this lecture and moving into something kind of different. But we want to definitely touch on this idea because it's a major idea in analysis, and it follows very closely, as you'll see, from the ideas of sequence. So let's go ahead and jump into it. We'll call this section 2.6, series of real numbers. And let's start with just some notation, which I'm sure you have seen by this point in your math career, but in case you haven't, we'll say that if a sub n from n equals 1 to infinity is a sequence in R, and if P and Q are natural numbers with P being less than or equal to Q, then we can write this, we can use this notation. The sum of K equals P up to Q of A sub K is equal to A sub P plus A sub P plus 1 plus dot 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 plus A sub Q minus 1 plus A sub Q. So this is the so-called sigma notation because of the sum. The sum is a Greek sigma. So this is sigma notation, which you will undoubtedly have seen before. I'm certain you've seen this in calculus, if not elsewhere. So this is a convenient way, obviously, of writing sums, and it's just taken for granted when we're talking about series that you know this notation. So just want to make sure the level's set on that. Okay, so let's define a series of real numbers. Okay, so we'll let a sub n from n equals 1 up to infinity be a sequence of real numbers. And we'll let s sub n from n equals 1 up to infinity be the sequence obtained from a sub n, where for each n and n, for each natural number n, S of n in this sequence is defined as the sum from k equals 1 up to n of a sub k. Okay. All right, so we've got a sequence a sub n of real numbers, and we've got this other sequence s of n, and s of n is a sequence that's derived based on the sum of the terms of the a sub n sequence, right? So in particular, s sub n is a1 plus a2 plus dot 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 plus an. S of n plus 1 would be a1 plus a2 plus dot 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 plus a sub n plus a sub n plus 1, right? And so the sequence S of n is called an infinite series. It's called an infinite series, right? Or we typically would just refer to it as a series, right? So it's called an infinite series, and it's denoted by either this, and it's denoted by, typically just by the sigma notation, k equals 1 to infinity of a sub k. Or, less concisely, you could write a sub 1 plus a sub 2 plus dot 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 plus a sub n plus dot dot dot, right? So it's an infinite sum, right? And the terms of this S sub n sequence are called the nth partial sums of the series. The S sub n terms are called the nth partial sums of the series. Okay. Right, and it's also called the nth term of the series. Okay, and so if you think about it, S1 is just A1. S2 is A1 plus A2. S3 is A1 plus A2 plus A3. Right, and so on. So these are the nth partial sums of the terms of this sequence. Okay, and then this sequence together is called an infinite series, or just a series. Okay, and so that's what we mean by series in real analysis. Basically just infinite sums. So you've certainly seen infinite sums back in calculus 2, I want to say is calc 2. And you would have gone through lots of convergence tests and things like that. Or, yeah, you would have gone through a bunch of different convergence tests for these types of things. And in real analysis, they obviously get a more thorough treatment, although not quite yet. Again, we're just kind of appending this to the end of our sequence section just because it's relevant, and it naturally follows from a lot of the machinery that we've built up over the past 9 lectures. So let's do an example. Let's take a look at an example. Famous example. This is the geometric series. So let's let r, absolute value of r, be less than 1. Then the sum, k equals 1 to infinity of r to the k power, is called the geometric sequence. Called the geometric sequence. Oh, sorry, series. That's a series. It's called the geometric series. Right, and so let's take an example of an nth partial sum. We'll say S of n. Right, S of n is going to be equal to the sum from k equals 1 up to n of this r to the k. So it's going to be r to the first power plus r squared plus r cubed plus so on, all the way up to r to the nth power. Okay. Now, this series does converge. Let's go ahead and show that. And this may be one you've seen before, but I always think this is a nice little derivation. So we'll start by rewriting this. So S sub n is equal to r plus r squared plus dot 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 plus r to the nth power. Okay. Now we can take this series here and we can multiply both sides by r. Right, so we'll call this equation 1. And then equation 2 will be this one, r times S sub n. And so instead of r, I have r squared. Right, and instead of r squared, I have r cubed. So on, all the way up to rn plus 1. We'll call this equation 2. Right, so I just start with the nth term of, or the nth partial sum, and then I multiply both sides by r. Now if I subtract 2 from 1, yep, 2 from 1. Right, so if I say S sub n minus r times S sub n, what do I get? Well, it's going to be this thing, so it'll be r plus r squared plus dot 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 plus r to the nth power. All right, and then minus all of these, so r squared plus r cubed plus dot 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 plus r to the n plus 1. Okay, and if you look at this, you can see that the r squared terms are going to drop out, the r cubed terms are going to drop out, the r to the nth power is going to drop out, and what I'm going to be left with here is r, this guy, minus this guy. Okay, and so I have what? I have S sub n minus r times S sub n equals r minus r to the n plus 1 power. Okay. Now remember, we're trying to come up with a nice way to write s sub n, so I can factor here, and so I have 1 minus r times s sub n is equal to r minus r to the n plus 1 power. And so that means that s sub n is equal to r minus r to the n plus 1 power over 1 minus r. Okay. Now, previously, when we were talking about sequences, we came across a theorem that says, so previously, we would have seen this, and you just go back 2 lectures, I think, and you would see this. Previously, we would have seen that the limit as n goes to infinity of r to the n is equal to 0 when r in absolute value is less than 1. Right, so like 1/2 to the nth power, the limit of that is 0. Okay, and so we can use that fact here, right? So the limit as n goes to infinity of s sub n would be equal to the limit as n goes to infinity of this thing, r minus r to the n plus 1 over 1 minus r, right? And so specifically this piece here, r to the n plus 1, that's going to converge to 0 as n goes to infinity. So this is going to be equal to r over 1 minus r. Okay, and so r is just a fixed number, right? In this case, r is just the common ratio here of the geometric series, and so it's a fixed number, and so this series is going to converge to this. So this series will converge to r over 1 minus r when the absolute value of r is less than 1, right? Now it's very important, right? It doesn't always converge, but specifically when r is between -1 and 1, then we do have a convergence, right? The series, the sum, will converge to this number, whatever this ratio r over 1 minus r. Now, what happens when r is outside of 1 in absolute value? So what happens when the absolute value of r is greater than 1, or greater than or equal to 1? Well, you can just kind of look at the previous limit, right? Limit as n goes to infinity of s sub n. Again, it will be the same. It'll be the limit as n goes to infinity of r minus r to the n plus 1 over 1 minus r. Now, what's going to happen to this thing? Well, the r's are okay, right? This piece and these in the new denominator, but this piece here is going to grow, right? It's going to get very large. Specifically, it's going to become a very well. It's going to approach negative infinity. That's going to go to negative infinity as n grows, right? So you've got r, some number, minus some huge number, right? And so this thing is just going to diverge to negative infinity whenever r is outside of 1 in absolute value, right? So the series will diverge when r is greater than or equal to 1. So it converges inside of 1, diverges outside. All right, very cool. Very cool. Okay, another example. And there's different ways to show these things converge or to show that they diverge. So we're just touching on a couple of different ways. And then towards the end of the lecture, we'll get to like a very specific criteria for this. But how about we talk about what's called the alternating harmonic series. Okay, so consider this guy. The sum as k goes from 1 to infinity of -1 to the k plus 1 power over k. So this will be, so when k is 1, this will be -1 squared, which is 1 up top and then 1 on the bottom, so just 1. When k is 2, it'll be -1 to the 3rd power, so it'll be minus actually 1/2. Right, and then it'll be plus 1/3 minus 1/4 plus 1/5 minus 1/6. plus dot dot dot, so on. Right, so it's called alternating and it's harmonic. It's a harmonic series basically. 1 plus 1/2 plus 1/3 plus 1/4. That's harmonic series. This one's alternating, meaning the signs alternate. Now it turns out this series converges to the natural log of 2. Converges to the value of ln2. Now, there's probably different ways to get to it, to get to that fact. But one of the easiest ways, and well, easy if you can remember your Taylor series, one of the easiest ways to see this is to use a Taylor series expansion, right? So if you consider the Taylor series expansion of the natural log of 1 plus x, and we're going to do this around 0. Okay, if we do this, so if you may not remember this, you can look it up, but the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus and so on. And it's ultimately equal to the sum as k goes from 1 to infinity of -1 to the k plus 1 over k times x to the k. All right, so this is the Taylor series expansion of ln x plus 1 around x equals 0. Okay, and this is something you would have come across in Calculus 2 probably. Yeah, I would say Calculus 2. Most, I would say 90% of the time, a Calc 2 course will cover this material, but it may be kind of vague in your mind. This isn't something you use all the time, so you can just look this up. It's pretty cool. But obviously, if you look at this, this looks an awful lot like, I mean, if you just look at the series here, it looks an awful lot like our alternating harmonic series, right? Now, it turns out that this is going to be valid when x is between -1 and 1. So this expansion is valid when x is, what we'll say, in the interval -1 to 1. Okay, and specifically when x equals 1, you can see what happens here. I've got ln of 1 plus x is ln of 2, and that's equal to 1 minus a half plus a third minus a fourth plus a fifth minus a fourth plus a fifth minus a sixth plus dot dot dot, and in general it's equal to the sum from k equals 1 to infinity of -1 to the k plus 1 over k, and now instead of x to the k, I just have 1 to the k, so it's just 1, I can leave it off. And so this is our alternating harmonic series, right? And we've just shown that this infinite sum, this infinite series, is equal to this value, ln2. Kind of nice, kind of remarkable. Okay, so those are two examples of converging series. Let's see an example where a series doesn't converge. Okay, so let's see an example where the series doesn't converge, and that would be something like, I mean, here's an example. There's lots of them, infinitely many of them. K equals 1 to infinity of -1 to the k power. Yeah, I could certainly write this as an infinite series. There, you know, I could do partial sums of this, but what happens when I try to add the whole shebang up? Well, let's talk about the nth partial sum here. It's equal to the sum of k equals 1 to n of -1 to the k power. Now, this is going to be like -1 plus 1, -1 plus, you know, so think about what this is. So this is like -1 to the first plus -1 squared plus -1 cubed plus -1 to the fourth plus dot 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 plus -1 to the nth. So this is -1 plus 1 plus -1 plus 1 plus dot dot dot. So you can see it's undoing itself, right? And so basically S of n is equal to either 0 or 1, right? It depends on where the series ends. It depends on whether basically n is odd or even. If n is even, then the sum is 0. If n is odd, then you get like -1 plus 1 minus 1, which is just 1. Right? So if in this case n is odd, right? And so this series diverges. Okay. So these are examples of infinite series, and a couple of examples where we have convergence, and this example where we have divergence. Okay, so again, a lot of focus in analysis can be put on series. We're not going to touch on it here. We're going to switch gears after this lecture, but one of the biggest connections that infinite series has with sequences is the following theorem. And this is a theorem that provides necessary and sufficient conditions for convergence of a series. Okay, so this theorem states that the series sum from k equals 1 to infinity of a sub k converges if and only if, given epsilon greater than 0, there exists an n naught natural number, right, such that what? Well, such that the absolute value of the sum from k equals n plus 1 to m of the series is less than epsilon, and that this needs to be true for all m greater than n greater than or equal to n naught. Right? So the series converges if and only if, for all epsilon greater than 0, there exists some natural number such that when I go out into the sequence, the absolute value of the partial sum from n plus 1 to m is less than the given epsilon. So i.e. arbitrarily small, right? And so the idea here is it's possible for me to go out far enough into the series so that I can find an n naught where the sum of the terms beyond n naught are arbitrarily small, smaller than any given epsilon. Okay. So that's hopefully kind of intuitive, right? If the series is going to converge, then as I go really far out into the series and I start summing terms in the tail of the series, those sums better get arbitrarily small, right? Like my first, S of n is going to be the sum of the first n terms, right? S of n plus 1 is going to be the sum of the first n terms plus the next term, right? What this is talking about is going way out into the series and just summing from here forward, right? So this would be like a sub n plus 1 plus a sub n plus 2 plus dot 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 plus a sub m, right? So where these two, n and m, can be arbitrarily far apart, right? But the point is I need to be able to find an n naught such that I can go out here such that all the terms beyond n naught, when I add them together, they're arbitrarily small. That should be intuitive. That has to happen, otherwise the series is certainly going to diverge. As I get further out into the series, the sums have to get smaller, right? Okay, so you're kind of basically lobbing off the first part of the series and saying, okay, if I'm far enough out, this sum better get small, right? So that's the idea of the proof, that's the idea of the theorem. The proof kind of follows this concept pretty closely. Let's talk through the proof. And the proof falls back on Cauchy sequences, as you can probably imagine, but let's see what this looks like. So for the proof, we'll start by just noting that the mth partial sum would be what? be a sub 1 plus a sub 2 plus dot 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 plus a sub n plus dot 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 plus a sub m, right? So again, we're assuming that m is greater than n, right, as the theorem stipulates. So this is the mth partial sum, and what's the nth partial sum? Well, it's just going to be this part, right? The absolute value of the nth partial sum. Okay, so if I were to take s sub m minus s sub n, what do I get? Well, I have a sub 1 plus a sub 2 plus dot 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 plus a sub n plus dot 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 plus a sub m minus a sub 1 plus a sub 2 plus dot 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 plus a sub n. All right. And you can obviously see the a sub 1 drops out, the a sub 2 drops out, the a sub n drops out. And so what I'm left with is the absolute value of a sub n plus 1 plus a sub n plus 2 plus dot 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 plus a sub m. Right? And this is the absolute value of the sum from k equals 1 up to m of a sub k. Right? This is the sum that specifically has to be less than epsilon as per the theorem. Right? If you look at the theorem, this is the thing that needs to be less than epsilon. Right? Well, this is stipulating a Cauchy sequence, isn't it? Right? So this is a Cauchy sequence, right? And we saw in the previous lecture that all Cauchy sequences must converge. All Cauchy sequences must converge, right? And so if this series converges, that means it's obviously going to have to be less than any arbitrary epsilon. It's possible for me to choose n and m such that I can make that thing less than epsilon, right? So it must converge. All right. Now, because of the way this proof works, specifically the way that it references a Cauchy sequence, this thing is usually called the Cauchy criterion, right? So this is usually called the Cauchy criterion for convergence of a series. All right. Right, and specifically just because, I mean, implicitly you're building out a Cauchy sequence, right? You're finding terms and showing that they must be Cauchy. Okay, let's do an example here where we use this. Let's see an example. So let's consider the sum from k equals 1 to infinity of 1 over k. Right, so let's consider two partial sums. So first of all, we know this does not converge, and we're going to use the Cauchy criterion to show it. All right, so consider two partial sums. So we've got s of 2n, which would be 1 plus 1 half plus dot 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 plus 1 over n plus dot 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 plus 1 over 2n. Right, and then we've also got s sub n, which is just this piece, 1 plus 1 half plus dot 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 plus 1 over n. Okay, now if I subtract s of n from s of 2n, then I get s of 2n minus s of n equals 1 plus 1 half plus dot 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 plus 1 over n plus dot 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 plus 1 over 2n minus, and then 1 plus 1 half plus dot 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 plus 1 over n. Right, and as before, everything kind of cancels out except for 1 over n plus 1 plus 1 over n plus 2 plus dot 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 plus 1 over 2n. Okay, so something to notice here, right, would be, first of all, how many terms are here? N terms. Okay, and second, notice that 1 over n plus 1, this is a larger number. This is greater than 1 over n plus 2, isn't it? Right? As the denominator gets smaller, this number gets smaller. Right? So 1 over n plus 1 is greater than 1 over n plus 2, which would be greater than 1 over n plus 3, and so on, all the way down to 1 over 2n. Right? So each term, each of these n terms is at least as large as 1 over 2n. Okay? So what does that mean? Well, the implication here is that s sub 2n minus s sub n must be greater than n times 1 over 2n. Right? This one is bigger than 1 over 2n. This one is bigger than 1 over 2n. This one is bigger than 1 over 2n. This one is equal to 1 over 2n. So we'll say greater than or equal to. Right? And so that means that s sub 2n minus s sub n is greater than or equal to 1/2. Now, that's obviously not a Cauchy sequence because n is just an arbitrary index, right? So no matter how far out I go, you're always going to have these gaps that are greater than or equal to 1/2, right? So a Cauchy sequence, the terms have to get closer and closer together. In this case, the terms don't get closer and closer together. Okay, so this is obviously not a Cauchy sequence, and so that being the case, the series does not converge. So the sequence of nth partial sums is not Cauchy, and the series does not converge. Okay, so it's a very clever way to kind of show this stuff, right? In order for the series to converge, the series of nth partial sums has to be Cauchy, and these are not. Okay, and then a nice little follow-on theorem to that one is this guy. Okay, so if the sum from k equals 1 to infinity of a sub k converges, if this series converges to a finite number, then the limit as n goes to infinity of a sub k must equal 0. So, I mean, again, this is hopefully kind of obvious. If the series converges, then the terms of the sequence must become arbitrarily small, right? Like I can't keep adding big numbers together and have the series converge, right? If I add an infinite number of numbers together, they're going to have to get very, very tiny very quickly, right, in order for the series to not blow up. And so that's what this theory is saying. Right, now the proof follows from the Cauchy criterion. And we won't go into it in detail, but, you know, basically, since a sub k is just s sub k minus s sub k minus 1, right? The kth term is just the difference between the kth partial sum and the k minus 1 partial sum. Then the theorem, I mean, if you set it up like this, the theorem follows directly from Cauchy's criterion. So since this is true, the theorem follows directly from Cauchy's criterion. Okay, and I realize that's not really a proof, but sometimes I just want to leave a little bit for you guys to do, but so see if you can flesh that out. Okay, awesome. So that's where we'll leave behind sequences for a moment. I mean, obviously it'll still be in the background of the work we're doing, but we're going to shift our attention to some newer topics, things you definitely haven't heard of unless you've taken analysis before, and that's going to be topics surrounding point sets, so the structure of point sets, and get into some topological kinds of concept, open and closed sets, compact sets, contour set. Very interesting stuff. I know when I took analysis for the first time, this was a super interesting section, and I hope you also find it interesting. Until then, take care.